On January 9th, 2007, Steve Jobs walked onto a stage in San Francisco holding a device that 48 hours earlier had refused to make a call. The engineering team had worked through the night swapping prototype boards, reflashing firmware, praying that the demo would hold. And for 90 minutes, it did. The audience cheered. The stock climbed. The narrative of revolutionary genius was sealed in glass and aluminum. But that narrative is a lie, or at least it is a carefully edited version of a story that nearly ended in a boardroom surrender. The iPhone revolution almost failed, not because the market wasn't ready, not because the technology was too early. It almost failed because of a single, stubborn design decision that every engineer inside Apple knew was a disaster, and that Steve Jobs refused to abandon. Here's the paradox that the official story buries. The most successful consumer product in history was nearly killed by the very thing that made it beautiful. The design that defined a decade was the same design that, in early 2006, had the project on life support. The question is not how the iPhone succeeded. The question is how it survived its own creation. You have heard the myth of the click wheel. Steve Jobs, legend says, initially wanted an iPod with a phone bolted on, controlled by the familiar scroll wheel that had made the iPod a cultural artifact. But the engineers who actually built those early prototypes tell a different story. They describe a device that was a mess, a feking mess, in the words of one engineer who handled the prototype. Entering a phone number on a click wheel required 15 thumb movements. Sending a text message was an exercise in rage. The click wheel concept was not a clever starting point. It was a dead end that wasted 18 months. And yet, here is where the myth gets dangerous. The click wheel failure is often told as a story of visionary pivot. Jobs, the narrative goes, realized the touchscreen was the future and bravely abandoned his own idea. But that version erases what happened next. Because when Apple abandoned the click wheel, they did not replace it with a finished touchscreen. They replaced it with a different set of problems so severe that the project nearly collapsed a second time. The touchscreen prototype that replaced the click wheel had its own fatal flaw. The glass overlay was too thick. The capacitive sensors could not register a light touch. Users had to press hard, and even then the response was erratic. The first public demo units, the ones Jobs held on that January stage, were carefully selected from a batch that worked. The rest were sitting in a lab, their screens unresponsive, their internals overheating, their batteries lasting less than 3 hours. This is the moment most history books skip. By the spring of 2007, Apple had a product that looked revolutionary on camera and behaved like a prototype in real life. The board had seen the failure rates. The carrier partner, AT&T, had tested the device and flagged critical issues. The launch date was set for June, and the phone, as designed, was not ready. So what saved it? Not a genius stroke, not a last-minute innovation. A single counterintuitive design rule that the team had resisted for months, a rule that once applied, transformed a failing product into a cultural singularity. And the person who enforced that rule was not Steve Jobs. It would be satisfying to name a single hero here, a lone engineer who saw the flaw and fixed it against all odds. But the real story is messier. The design that saved the iPhone was not a discovery. It was a subtraction. And subtraction, in a culture that worships addition, is the hardest move to make. The original iPhone design, as it stood in early 2007, had a feature list that would make any product manager dizzy. A full web browser, a visual voicemail interface, a music player, a camera, a Maps application, and buried in the spec sheet a requirement that the device must feel like a seamless object, not a collection of parts. That last requirement, the seamless object, was the one that nearly killed everything. To achieve seamlessness, the industrial design team, led by Jony Ive, had insisted on a unibody construction. The screen would be bonded directly to the aluminum frame. There would be no bezel, no gap, no visible seam between the glass and the metal. It was beautiful. It was also impossible to manufacture at scale. The bonding adhesive failed under heat. The glass cracked under pressure. The aluminum frame flexed enough to misalign the internal antenna. This is the moment when the story inverts. The thing that saved the iPhone was not a feature added, but a feature removed. This is exactly the kind of counterintuitive edge that the crowd misses, the same way retail traders chase indicators while the quants subtract noise. If you want more of these hidden patterns, the moves that feel wrong but win, subscribe and let this channel be your quiet edge. And tell me in the comments, what is one area of your life or work where subtraction would be the answer, but you have been afraid to make the cut? By March, Apple had produced fewer than 500 working prototypes, and half of those had failed environmental testing. The project was bleeding money and time. Executives began preparing contingency plans, a scaled-down launch, a delayed release, or in the worst case, cancellation. This is where the psychological inversion begins. The institution, Apple, with its billions in cash and its world-class engineering talent, was trapped by its own definition of quality. They believed that a seamless object meant a perfect union of materials. They believed that the user would perceive any gap as a flaw. They believed that beauty required purity, and that belief was wrong. The fix, when it came, was not a technological breakthrough. It was a refusal to accept the premise that seamlessness required physical bonding, a refusal to believe that the user cared about the manufacturing process, a refusal to keep adding complexity to solve a problem created by complexity in the first place. You have felt this moment. You have worked on a project where every problem spawned a new feature, and every feature created two more problems. You have watched the scope balloon until the original purpose was unrecognizable. You have been in the room where someone finally said, "What if we just stop adding things?" That person, inside Apple, was not an executive. It was a mid-level engineer named Greg Christie. Christie was not a designer. He was a software interface engineer who had been at Apple since the early 90s. He had worked on the Newton, the failed personal digital assistant that taught the company a brutal lesson about the cost of premature complexity. And when he looked at the iPhone prototype in early 2007, he saw the same pattern repeating: a touchscreen that required too much pressure, a software keyboard that registered phantom taps, a notification system that interrupted every task, a hardware design so rigid that it left no room for the software errors that were inevitable. Christie wrote a memo that circulated quietly through the engineering team. It was not a dramatic manifesto. It was a list of 18 specific problems, each with a proposed deletion. Remove this feature, change this assumption, simplify this interaction. The memo did not change everything overnight, but it planted a seed. And the seed grew into a rule that would define not just the iPhone, but the entire mobile industry for the next decade. The user interface must require the minimum possible input force. The screen must respond to a brush, not a press. That rule seems obvious now. In 2007, it was radical. Every competing smartphone, from the BlackBerry to the Palm Trio, required deliberate physical pressure. Buttons clicked, styluses pressed. The user had to commit force to every action. Christie's rule inverted that assumption. It said the device should meet the user halfway. It said the device should be passive, not active. And that inversion created a cascade of consequences. If the screen required only a light touch, then the glass had to be thinner and more responsive. But thinner glass shattered more easily. So the team needed a new type of glass, one that could be chemically strengthened. That search led them to a company called Corning, which had invented a material called Gorilla Glass years earlier, but had never found a commercial application for it. The Gorilla Glass decision is often told as a happy accident. An executive remembered a forgotten material in a basement lab, but that story erases the tension. Corning had shelved Gorilla Glass because it was too expensive to produce at the scales Apple required. The negotiations were brutal. The contract nearly fell through twice, and even after the deal was signed, the yield rates were so low that the first production runs cost Apple more than 3 times the budgeted amount per unit. But the rule held: minimum input force. The device must respond to a breath. What no one predicted was that the same rule would solve a second problem: the antenna. The iPhone's antenna was embedded in the aluminum frame, a design choice that made the device thinner at the cost of signal reliability. When users held the phone in a certain way, the now infamous death grip, the signal dropped. The engineering team knew this before launch. They had tested it. They had flagged it. And they had no fix because the aluminum frame was too structurally integral to the design to change. But the glass back, introduced as part of the Gorilla Glass solution, changed the antenna dynamics. Glass is radio transparent in a way that aluminum is not. By moving the antenna away from the metal frame and into the glass region, the signal loss was reduced. Not eliminated, but reduced enough to ship. The iPhone did not succeed despite its design. It succeeded because of a single constraint that forced a cascade of subtractions. But that constraint was almost never applied, and the person who applied it was not the visionary CEO. It was an engineer who had seen a project fail before and refused to watch it fail again. You are not just a user of this device. You are the reason the constraint was enforced, because Christie's rule was not about engineering. It was about empathy. It was about asking, what does the person holding this thing actually need? And the answer was not more power, more features, more seamlessness. The answer was less friction. The industry learned the wrong lesson. After the iPhone succeeded, every competitor tried to copy the outcome. The glass slab, the minimal interface, the gesture controls, but they did not copy the process. They did not adopt the rule of minimum input force. They did not ask what could be removed. They asked what could be added. That is why the second iPhone almost failed too, but that is a story for another video. The industry learned the wrong lesson. You just saw the real one. The most powerful move is often subtraction, not addition. That is the kind of inversion that gives you an edge the quants can't code for. If you want to catch these hidden patterns before they become obvious, subscribe. This channel is built for the ones who notice what others overlook. And drop the word remove in the comments if you've ever cut a position and watched it save your portfolio. The last prototype that bore the scars of the near collapse sat on Jony Ive's workbench for months after the launch. Its screen was cracked from a drop test that had gone wrong. Its aluminum frame was scuffed from the 100th reassembly. Ive did not throw it away. He kept it as a reminder of the moment the project had nearly surrendered. That prototype is now in a private collection, but the lesson it holds is not private. It is encoded into every iPhone that followed. The glass that bends under pressure, the interface that waits for you, the device that does not demand your force. The question is not how the iPhone survived. The question is why the most obvious fix, remove the friction, subtract the complexity, took a near-death experience to be adopted. Because the people who could see the fix were not the ones in charge. They were the ones who had failed before. And failure, if you survive it, teaches you what addition never will. You have held that phone. You have felt that weight. Tell me in the comments, what design compromise did you never notice until now? The prototype with the cracked screen was not the only artifact that told the truth about the near collapse. There was another one, less famous, sitting in the archives of the design studio. A single logic board pulled from a unit that had failed thermal testing. The board was warped. The solder joints had fractured under the heat generated by the processor, which was running at a clock speed that had been pushed higher to compensate for the software's sluggish response to the unresponsive screen. The engineers had added a thicker heatsink, then a fan, then a software throttle. Each addition created a new problem. The heatsink made the phone thicker. The fan was too loud. The software throttle made the interface lag, which made the screen feel even worse. The team was adding solutions to problems created by previous solutions, and the device was becoming a monument to its own contradictions. This is the point in the story where the institution's assumption that more engineering solves more problems reached its logical dead end. Apple had the best hardware engineers in the world. They had unlimited budget. They had the authority to redesign any component. And yet the more they engineered, the worse the device became. The phone in March 2007 had more parts than the phone in January 2006. It had more features, more complexity, more failure modes. It was, by any objective measure, a worse product. And that is exactly what Greg Christie saw when he wrote his memo. He did not propose a new technology. He did not suggest a new component. He listed 18 things to remove. One of them was the heat sink itself. His logic was simple. If the processor generates less heat when it is not fighting an unresponsive screen, remove the screen problem first, then see if the heat sink is still needed. It was not a glamorous insight. It was the kind of thought that only becomes visible when you stop believing that the next edition will be the one that works. You have been in this meeting. You have sat in a room where everyone agrees that the problem is complex, and the solution must be equally complex. You have watched a team spend 3 months building a workaround for a problem that could have been solved in 3 days by removing the thing that caused it. and you have felt the quiet embarrassment of realizing that the simplest fix was available from the start, but no one wanted to say it because it sounded like giving up. The corrosion on a single prototype board told the story of that institutional blindness more clearly than any executive memo ever could. The board was from unit number 411, one of the early production validation tests. The environmental chamber had subjected it to high humidity and temperature cycling, simulating a year of use in a tropical climate. The board failed, but the failure was not in the processor or the memory or the antenna. The failure was in a tiny capacitor that had been added to filter noise from the display driver. The capacitor was unnecessary. The noise it filtered was created by the display driver's own power management circuit, which had been added to compensate for the thicker glass that required more voltage to register a touch. Remove the glass problem, and the capacitor, the power management circuit, the thicker driver, and the noise all disappeared together. One component, one assumption, one cascade of unnecessary complexity. And the evidence was etched into a warped green board that no one outside Apple has ever seen. The institutional pattern is the same in every domain. The more resources an organization has, the more it believes that problems are solved by adding more engineers, more features, more layers of abstraction, more management. And the harder it becomes to see that the problem itself was created by the last addition. Apple, in 2007, was not lacking talent or money or intelligence. It was lacking a cultural permission to stop. That permission came from a single line in Christie's memo. It was not a technical recommendation. It was a philosophical one, buried in the middle of the list. It read, "The device is finished when there is nothing left to take away." He was quoting Antoine de Saint-Exupéry, the French aviator and writer, who had said the same thing about aircraft design in the 1930s. A pilot does not need more instruments. A pilot needs fewer distractions. A phone does not need more features. A phone needs fewer interruptions between the user and the task. You have read that quote in 100 design blogs, but you have never seen it applied the way Christie applied it. He did not use it as a slogan. He used it as a test. Every feature on his list was examined under one question. Does this bring the user closer to their goal, or does it add a step? If it added a step, it was marked for deletion. The visual voicemail interface, which everyone in the company was proud of, was nearly cut because it required the user to tap twice instead of once. It survived only because Christie's own data showed that users preferred visual selection over sequential listening. But other features were not so lucky. The custom ringtone editor was removed. The video recording feature, which existed in early prototypes, was removed. The ability to run third-party apps, which the engineers had prototyped, was removed. The device launched with no app store, no video, no custom sounds. It was deliberately incomplete, and that incompleteness was its greatest strength, because every feature that was removed was a feature that could not fail. A ringtone editor that did not exist could not crash. A third-party app that was never installed could not drain the battery. A video recorder that was not shipped could not corrupt the file system. The phone shipped with fewer failure modes than any smartphone before it, not despite the removals, but because of them. The product team called it the stripped launch internally. The marketing team hated it. The carriers demanded more features. Competitors released phones with video recording, MMS, cut and paste, and a dozen other capabilities that the first iPhone lacked. The reviews were mixed. Tech journalists wrote headlines asking if the iPhone was a real smartphone or just a pretty iPod with a phone radio. The institution felt the pressure. The board asked why the product was being launched with so few features. And yet the stripped launch is what saved the project. Because the fewer the features, the more time the engineering team could spend fixing the ones that remained. The team that had been spread across 24 features was now concentrated on 5. The screen responsiveness improved. The battery life increased. The antenna signal stabilized. The software crashes dropped from multiple per hour to 1 per day. The phone that launched in June was not the phone that had been designed in March. It was a narrower, deeper, more reliable version of itself. You have seen this dynamic in your own work. You have launched a project that felt incomplete, with features missing, with rough edges exposed. And you have watched it succeed because what was there worked. While competitors broke under the weight of everything they had promised, the iPhone did not win because it had more. It won because it had less, and what it had perfected. That is the inversion the institution will never teach you. The edge is not in accumulation, but in subtraction. What you choose to leave out becomes your moat. If you want to uncover more of these quiet patterns before the crowd catches on, subscribe so you do not miss the next reversal. Drop the word stripped in the comments if you have watched this dynamic play out in your own work or trades. But the institution did not learn the lesson. The second iPhone, released a year later, added the things that had been stripped from the first: video recording, third-party apps, GPS. The device was better. It was also more complex. And with that complexity came a new category of failure: the antenna death grip that plagued the iPhone 4. The same pattern repeating at a higher resolution. The same assumption that addition is progress. The same refusal to see that the problem was not the antenna placement. The problem was the belief that every problem has an engineering solution, when sometimes the only solution is to remove the thing that creates the problem in the first place. The logic board from Unit 411 was not discarded. It was placed in a clear acrylic box and stored on a shelf in the engineering wing, a quiet monument to the cost of complexity. Engineers who joined the team after the launch would walk past it during their first week, and someone would invariably stop to explain what the green board, with its tiny scorch marks and warped edges, represented. It represented the moment subtraction won. It represented the insight that no amount of additional resources could substitute for the discipline of removing what should not be there in the first place. You have held that phone in your hand. You have felt its weight, its balance, the way the glass meets the metal, with a precision that feels inevitable. That inevitability was not designed, it was excavated. Every millimeter of space inside the device was fought for, cleared of components that had once seemed essential. The battery was reshaped twice because the original design left voids that could not be filled. The speaker grill was moved 3 times because the first 2 positions interfered with the antenna. The home button was nearly abandoned because it consumed volume that the logic board needed. And in each case, the answer was not to make the device bigger. The answer was to make the component smaller, or find a way to do without it. The tolerance for subtraction extended to the software as well. The operating system, stripped of multitasking and background processes, had fewer moving parts than any mobile OS before it. The kernel could boot in under 30 seconds. The memory footprint was small enough that the device could run on a fraction of the RAM that competitors required. The system did not crash because there was nothing to crash against. The software was not designed for capability. It was designed for constraint. Steve Jobs understood this at an intuitive level. He had learned it from the original Macintosh, which had been built in a similar atmosphere of scarcity and subtraction. But the institution he built after the iPhone succeeded grew too large to remember that lesson. The company that launched the iPhone in 2007 had fewer than 20,000 employees. The company that launched the iPhone 12 in 2023 had more than 160,000. The complexity of the organization scaled faster than the complexity of the product, and with scale came the inevitable return of addition: more features, more models, more versions of the operating system, more teams competing for resources. The same pattern that nearly killed the first iPhone. The difference is that the first iPhone had a Greg Christie, an engineer with the authority of a failure behind him, who could say no. The later iPhones had committees, and committees by their nature say yes to everything that does not threaten the schedule. The subtraction muscle atrophied, but the product that survived the near collapse is still the foundation of everything that followed. Every iPhone since the original has been built on the same assumption. The user interface must require the minimum possible input force. The screen must respond to a breath. That rule has never been abandoned. It is the single thread that runs through 17 generations of devices, through changing screen sizes and processors and cameras and sensors. It is the fingerprint of the moment when someone refused to keep adding. The corrosion on that single prototype board is not just a historical curiosity. It is a mirror. It shows you what happens when an organization becomes too rich, too confident, too convinced that its own resources can solve any problem. It shows you the shape of a failure that was avoided by the narrowest of margins. And it asks you a question that no amount of engineering can answer. What are you adding right now that is creating the next problem you will have to solve?